Now the photoelectric effect seems to have complicated things further. Hopefully the remaining physicists will be able to give us some insight into what the final model shall be. Planck was the man who, in effect, shifted the beliefs on light from the so-called classical era to the newer quantum era.
Oh, you're too kind. I basically combined the existing formulae of Wien and Rayleigh to come up with my radiation theory, or formula, that shows the distribution of energy to be relative to its wavelength. While deriving this, however, I noticed that the energy would need to be theoretically coming in bits and pieces, and for this I needed a constant to figure out at what rate the energy was carried and at a certain frequency.
Okay, would you be able to tell us what this number was?
Yes, 6.625 times 10 to the negative 34. It's effectively the h in the E equals FH equation, where F is frequency.
And was there anything else that you set forward?
Yes, I was also the first person to put forward that light was both a wave and a particle at once.
Now we're going to speak to de Broglie. De Broglie's most famous words were that light acts like a particle on Monday, Wednesday, and Friday, as a wave on Tuesday, Thursday, and Saturday, and like nothing at all on a Sunday. De Broglie, tell us how you got started.
My brother's work on X-rays was invaluable help for me when writing my doctoral thesis, for which I received a Nobel Prize. Recherches sur la théorie des quanta. I built on the work of Einstein and Planck with my wave-particle duality stance on light, which I came to after many years of working with my brother and noticing that X-rays were definitely both particles and waves at once.
Okay, have you got any famous words that have been said about you, perhaps?
You threw yourself into the controversy raging round the most profound problem in physics and had the boldness to assert that matter had not only a corpuscular theory, but also a wave nature. Experiments later established the correctness of your view.
So, did you have any practical applications of mathematics?
Using Planck's findings on radiation, to apply the quantum hypothesis to the explaining of electromagnetic radiation of light. I also predicted that light from a distant source would bend towards the sun.
Well, come on, get into some of your more famous work that isn't, well, related to relativity.
Well, the thing is, that thing is what won me my Nobel Prize, was my study of the photoelectric effect. With this, I was able to justify the wave theory's inability to account for the effects first noticed by Planck, and as such supported the particle theory or model in my findings.
Whoa, slow down, Einstein.
The particle, these photons, would explain were knocked out with a greater intensity of light, but they didn't display any changes in energy.
I'm still not following you.
Increasing the intensity increased the number of photons hitting the material, so more electrons were knocked out and wavelength varied the energy carried by the photons.
Well, it seems Einstein was able to explain the photoelectric effect to some degree. There's still quite some dispute as to which model is accurate, the wave model or the particle model, or possibly even the dual nature model. It seems at the moment that any definition would be about as impossible as teleportation. So hopefully we can come to a final conclusion at the end of this.
We brought experimental verification to de Broglie's particle-wave duality theory. Quite fortunately, this gave the particle-wave duality theory a real shot in the arm.
I see. May I ask as to your garments?
No. We were also the first to apply Bragg's law of refraction to matter, such as electrons, and we were also the first to apply it to X-rays. Basically, using special apparatus, we had a vacuum in which electrons from a special heated filament could be accelerated towards a nickel plate. Behind this plate, an electron detector, or Faraday box, swung around in an arc. This meant that the electrons were in fact waves, and that Bragg's law could be used to calculate the atomic spacing in the plate. We were amazed to find that there were peaks and troughs in the electron beam that had now been scattered. Thank you. Christmas tree, what were you thinking? As son of the discoverer of the electron, J.J. Thomson, using my electron diffraction camera to bombard very thin pieces of metal foils and plates with an electron beam, at the other end one would find a series of concentric rings as one would find for light.
This seems to be very helpful to the theories of de Broglie.
People keep saying that, yes. As I've always said, observing light makes the wave structure break down into particles. Light effectively departs and arrives as a particle and travels as a wave. Unfortunately, they can never be observed as both types at one time. Now, observable in the double-slit experiment, the light departs the source in a straight line but spreads out like a wave via diffraction and returns to the particle state when they hit the screen and lighting up the areas the wave has taken it to.
Well, it seems like all three arguments have very legitimate founding, so it doesn't look like we're going to come to a conclusion today, though I must thank you for watching. I'm Matt Allard. Couldn't find any music for free that I figured would fit the end credits, and nothing in public domain seemed to work, so here. Doop doop dooby doo doop doop doo doop doop dooby doo doop doop doo.
If you think you can get away with not subscribing to Carpe Clunes, think again.